Hello everyone, and welcome. Today we're going to explore the fascinating world of arithmetic progression. On this first slide, I want to introduce our topic with enthusiasm. The title is Arithmetic Progression, and we might have a subtitle that gives a hint about what we'll cover. Over the course of this presentation, we'll look at what arithmetic progressions are, how to identify them, and some interesting applications. But for now, let's get started and enjoy this learning journey together. Now, let's look at the problem on this slide. We need to find the number of terms in this arithmetic progression: 100, 105, 110, 115, and so on, up to 500. To do that, we first recall the basic concept of an arithmetic progression, or AP, which is a sequence where each term increases by a common difference. Here, the difference is 5. Next, we use the formula for the nth term of an AP, which is a plus. n minus 1 times d in this case. The first term is 100, and the common difference d is 5. We set the nth term equal to 500, our last term, and solve for n this way. We can find out how many terms are in the sequence. Understanding how to find the number of terms is essential because it helps us analyze the sequence and solve related problems, like summing all these terms or finding specific terms. This example illustrates the practical application of the formulas we've been discussing, connecting the concept of AP to real problem-solving situations. Let's look at this first example: 2, 6, 18, 54, and so on. Notice how each term is obtained. Yes, by multiplying the previous term by 3. This pattern shows us how each number in the sequence is related to the one before it, which is a key idea when studying sequences. Now compare that to the second example: 1, 3, 5, 7. Here, instead of multiplying, we add 2 to get the next term. Both examples illustrate different kinds of relations between consecutive numbers. This brings us to an important point. A list of numbers like this, where each term is connected to the one before it through some rule or relation, is called a sequence. Recognizing these relationships helps us understand how sequences work and how to analyze them. Throughout this presentation, we'll see how identifying these patterns can reveal interesting properties and applications of sequences in various fields. Let's take a closer look at this sequence: 10, 15, 20, 25, and so on. Each term is obtained by adding 5 to the previous one. This pattern continues consistently throughout the sequence. Now, if we look at another example, like 4, 6, 8, and so forth, we see that this sequence of even numbers is also a perfect illustration of an arithmetic progression, or AP for short. So, what exactly makes a sequence an AP? Well, if you can form various terms of a sequence by adding a fixed number to the previous term, then that sequence is called an arithmetic progression. The key point here is the idea of an asterisk fixed difference between successive terms. For example, in the sequence 2, 4, 6, 8, each time we add 2, which remains constant. That's the hallmark of an AP. Understanding this concept is important because it helps us recognize patterns and predict future terms in a sequence, which is very useful in many areas of mathematics and real-world applications. This concept ties into our broader theme of recognizing patterns and understanding how sequences develop over time. All right, let's look at this sequence: a plus d, a plus 2d, a plus 3d, and so on. This pattern is actually the foundation of an arithmetic progression, or AP for short. Here, each term is generated by adding a common difference, which we'll call d, to the previous term. Now, in this particular example, we're setting d to 1. That means each term increases by 1 from the previous one. So if we start with the next term is a plus 1, then a plus 2, then a plus 3, and so forth. This simple setup helps us understand how an arithmetic progression works. Each term is just a fixed step away from the one before it. Recognizing this pattern is key because it appears in many real-world situations, like evenly spaced schedules or salary increments. Remember, the main idea here is that the sequence progresses in a consistent, predictable way, which makes it easier to analyze and work with mathematically. This is a fundamental concept that will help us explore more complex sequences later on. Let's take a closer look at what an arithmetic progression is. Here, A represents the very first term of the sequence. Then, D is called the common difference, which means the amount we add each time to get to the next term. So starting from the next term is a plus D, then a plus 2D, and so on. Each subsequent term increases by this same difference, which is what makes the sequence arithmetic. You can see the pattern continues infinitely, and the nth term of this sequence is written as a plus, n1d. The general form of an arithmetic progression is a way to express this pattern in a compact, formulaic way. It helps us easily find any term in the sequence without listing all previous terms. Understanding this form is key because it links directly to many real-world situations, like savings plans or population growth, where things increase or decrease at a steady rate. So, when we talk about the general form, we're essentially describing the entire sequence with a simple formula, making it a powerful tool for analysis and problem-solving. Let's look at how to find the fifth term in this sequence. Each time we want to find the next term, we add a constant value, which we call the common difference, or D. For example, the second term is the first term plus D. The third term is the first term plus D plus another D, so it's the first term plus 2 times D. Similarly, the fourth term is the first term plus 3 times D. So, in general, to find the nth term, we take the first term and add the common difference multiplied by n-1. Now let's look at the sequence 3, 7, 11, 15, 19, where the common difference D is 4. Notice how each term increases by 4 from the previous one. This constant increase is what makes it an arithmetic progression. The first term, which we call it, is 3. To get the next term, we simply add 4. The recursive formula for this sequence can be written as each term equals the previous term plus D. But we can also express the nth term directly as an equals a plus n-1 times D. So, whenever we're working with an arithmetic progression, knowing the first term and the common difference allows us to find any term in the sequence easily. Hence, it's solved. Therefore, a sub n equals 24. We can see this written as a sub n equals 2 plus 22. Or, more clearly, a sub n equals 2 plus the product of 11 and 2. This simplifies to 2 plus the product of 12 minus 1 and 2. Now, recalling the formula for the nth term of an arithmetic sequence, a sub n equals a plus n-1 times D. Given that a equals 2, D equals 2, and n equals 12, we can now find a sub n. So plugging in these values, a sub n equals 2 plus 12 minus 1 times 2. This is a great example to see how the formula works in practice and connect it back to our overall understanding of arithmetic sequences. Let's look at this example to understand how to determine if the given terms form an arithmetic progression. Since the differences between consecutive terms are the same, we can see that the terms are in AP. For instance, the difference between the fourth and third terms is 14 minus 10, which equals 4. Similarly, the difference between the third and second terms is 10 minus 6, also 4. And the difference between the second and first terms is 6 minus 2, again 4. Because all these differences are equal, we confirm that the terms 2, 6, 10, 14 are in AP. Now, note that the first term here is 2. To find the common difference, we look at the differences between terms, which in this case is 4. This pattern of equal differences is key to identifying an arithmetic progression. And this concept helps us understand how sequences behave and how to verify if a sequence is in AP. Now, moving on, we'll explore how to check if a given term actually belongs to an AP or not. Let's look at this slide. We start with the key idea that if a series is an arithmetic progression, then the differences between consecutive terms are constant. That's why we see the expression a 2 minus a 1 equals a 3 minus a 2. Now, plugging in the values, we get 2k equals 18, which simplifies to k equals 9. This is our first key result. Next, we see some other equations involving k, like k plus k equals 12 plus 1 plus 5, which simplifies to 2k equals 18 again, confirming our earlier result. Then, there's the equation k minus 5 equals 12 minus k plus 1, and this simplifies to 2k equals 18 once more. Similarly, the last equation, k minus 1 minus 4 equals 12 minus, and then in parentheses, k minus 1, which again simplifies to the same result for k. This consistency shows that regardless of how we set up our differences, the value of k that makes the series arithmetic is 9. We also see the notation d1 equals d1, emphasizing that for an arithmetic series, the differences are equal throughout. Finally, the series given is 4, k1, and 12. To determine whether this series forms an arithmetic progression, we need to find the value of k that makes the differences equal. And from our calculations, that value is k equals 9. This problem highlights how understanding the common difference helps us identify whether a series is an arithmetic progression, and solving these equations confirms the value of k needed for that. Let's take a closer look at the formulas for the sum of n terms in an arithmetic sequence. The first formula shown is one way to calculate the sum, using the first term, the number of terms, and the common difference. It's written as Sn equals n divided by 2, multiplied by the quantity 2a plus, n plus 1 times d. Then, there's an alternative expression for the sum, which states that Sn equals n times the average of the first and last terms. This is a very useful way to think about it, because it highlights that the sum is essentially n times the mean of the first and last terms. Now, the last term in the sequence, which we often denote as, is given by a plus. n minus 1 times d. Recognizing this helps us understand how the sequence progresses and how to find the last term directly. Finally, the general formula for the sum, often called the sum of an arithmetic series, is expressed as the number of terms, n, multiplied by the average of the first and last terms. This approach simplifies calculations, especially when you know the first and last terms rather than all individual terms. Overall, these formulas are fundamental because they give us flexible ways to find the total of a series, whether we know the first term, the last term, or just the common difference. They really tie together the concepts of sequence progression and summation beautifully. Let's take a closer look at this formula for the sum of an arithmetic series, which is represented as Sn equals n over 2 times 2a plus, n minus 1 times d. This formula essentially gives us the sum of the first n terms in an arithmetic sequence, where a is the first term and d is the common difference. Now, if we write this out, it becomes clear that 2 times Sn is equal to the sum of multiple identical terms, specifically 2a plus, n minus 1 times d, repeated n times. Think of it like stacking the same amount repeatedly. This helps us see the structure of the sum more clearly. Next, if we add equations 1 and 2, which are the original sum and its reverse, we get a new perspective. Sn equals the sum of terms starting from a, then a plus d, then a plus 2d, and so on, up to a plus n minus 1d. This step is crucial because it shows us the symmetry in the sequence. Finally, if we write out the sequence backwards, we observe that the sum remains the same. It's just the order of addition that changes. We see the terms as a, then a plus d, then a plus 2d, continuing up to a plus n minus 1d. Recognizing this symmetry helps us derive the general formula for the sum of the first n terms, which is foundational in understanding arithmetic series. So to find the number of terms in this arithmetic progression, we start by identifying the key components. First, we recognize that the total number of terms, n, is 81. We can see this written as n equals 81. Then, we break it down further. N is the same as 80 plus 1. Next, we look at the term just before the last one, which is n minus 1, and that equals 80. We also express n minus 1 as a fraction, 400 divided by 5. Multiplying both sides by 5 gives us 5 times n minus 1 equals 400. Rearranging, we have 400 equals 5 times n minus 1. To isolate n minus 1, we can add or subtract as needed, but here, it's clear that 500 minus 100 equals 5 times n minus 1. Simplifying, 500 equals 100 plus 5 times n minus 1. Now we recall the general formula for the nth term of an arithmetic progression. Equals a plus n minus 1 times d here. The common difference, d, is 105 minus 100, which equals 5. The first term, is 100, and the last term is 500. Putting it all together, our goal is to find n, the total number of terms. So, solving these equations step by step, we see that the total number of terms from 100 up to 500, increasing by 5 each time, is 81. This confirms that the sequence contains 81 terms in total. Let's walk through how we find the sum of the first 15 terms of this arithmetic progression. The total sum is 3690. First, notice that 3690 can be broken down into smaller parts for easier calculation. We see it's equal to 15 times 246, which suggests we can factor the sum as 15 multiplied by some value. Next, this becomes 15 times the sum of 24 and 232, which simplifies our calculation further. We rewrite this as 15 times 24 plus 29 times 8, because 232 is 29 times 8. Now, to make it even clearer, we can express this as half of 30 times the remaining value, multiplied by the sum of 2 times 12 plus 29 times 8, inside the brackets. This step introduces the formula for the sum of an arithmetic progression, which is Sn equals n divided by 2, times 2 a plus, n minus 1 times d here. Sn is the sum to n terms, O is the first term, and d is the common difference. In our case, the common difference d is 20 minus 12, which equals 8. The first term is 12. So the problem we're solving is to find the sum of the first 30 terms of this progression, which starts at 12, then 20, 28, 36, and continues onward. By understanding these key points, the sum formula, the common difference, and the first term, we can systematically calculate the total sum for any number of terms in the sequence. Let's take a closer look at this slide. First, we see the notation for the sum of the first 50 terms, which is represented as 50 times 202, and then similarly, 50 times the sum of 4 and 198. This illustrates how the sum of an arithmetic series can be broken down into these components. Now, moving to the formula for the sum of the first n terms of an arithmetic progression. That's Sn equals n over 2 multiplied by the sum of the first and the nth term, or more precisely, Sn equals n over 2 times 2a plus n minus 1 times d. This formula is fundamental because it allows us to find the total sum quickly once we know the first term, the number of terms, and the common difference. On the next line, we see the specific case where n minus 1 equals 99, which means n equals 100. This is important because it shows how we set up the problem for the sum of the first 100 terms. Then we multiply both sides by 2 to get 2 times n minus 1 equals 198. Simplifying further, we find that 200 minus 2 equals 2 times n minus 1, leading us to the key relationship. 200 equals 2 plus n minus 1 times 2. Next, we look at the nth term formula, which is equals a plus n minus 1 times d. The common difference, d, is calculated as 4 minus 2, giving us 2. The first term, is 2, and the sequence progresses as 2, 4, 6, 8, and so on, up to 200. This is a classic arithmetic sequence with a common difference of 2. Finally, the problem is to find the sum of these terms in the given arithmetic progression. The overall theme here is how to efficiently find the sum of a sequence when you know the first term, the common difference, and the number of terms, key concepts that help us understand summation in series. Let's take a closer look at how we can find the difference between any two terms in an arithmetic progression. As you can see from the formula, t, n minus t, k equals n minus k times d, this essentially tells us that the difference between the nth term and the kth term depends on the number of steps between them, multiplied by the common difference, d. When we break down the steps, we see that t, n minus t, k simplifies to n minus k, which makes sense because both terms are built from the initial term a plus multiples of d. Another way to look at this is to think of the difference as the difference between two specific terms in the sequence. A plus n minus 1 times d minus a plus k minus 1 times d. When we subtract these, the a's cancel out, leaving us with n minus 1 d minus k minus 1 d, which simplifies to the same n minus k. So, in essence, the difference between any two terms in an AP is just the difference in their positions, n and k, multiplied by the common difference d. This highlights how the sequence's regular spacing makes it straightforward to find differences between terms, regardless of their positions. This formula is fundamental because it connects the position of terms directly to their values, reinforcing the idea that an AP is a sequence with a constant difference, and that we can easily analyze differences between any two terms using this approach.